Hey everyone, today I would like to talk about my topic, which is polyaromatic hydrocarbon, thin film layers on glass, dust, polyurethane form surfaces. Presentation will go through four main parts: introduction, experiment, result, discussion, and the last one is conclusion. Start with the introduction part. Polyaromatic hydrocarbons or PH are type of chemicals made up of multiple rings. They are often found in indoor air and come from different places and natural sources such as coal or oil, things like burning stuff, and human-made sources like what gets dumped from waste plants or cooking in our kitchen. The chemical can stick to things or float in the air. To particular pH, naphthalene and benzopyrene are pretty common in household dust and films. They are also used in various industries. Being around these chemicals can be bad for our health. The amount of pH indoors depends a lot on the temperature and how humid it is. When it's hotter, more of these chemicals can get into the air, and humidity can affect how they get released in different ways. pH are a big deal because they can stick around for a long time, build up in the environment, and hurt our health and nature. So scientists are looking into how they stick to things, break down, and what they look like to understand what they do in the environment. My study, I'm checking out how naphthalene and benzopyrene behave on different surfaces and how they change over time to learn more about what they do in the environment. What will be experiments? The surface analysis such as FTIR and fluorescence were performed to analyze the evaporation on the surface of naphthalene and benzopyrene. In particular, the SPME-GCAMS analysis method was used to measure the dispersion of naphthalene and benzopyrene in the air. Part will be results and discussion. Every SAM analysis of two dust samples revealed distinct differences in shape and size distribution. Showcased in the figure, isodust exhibited a uniform size profile while SRM dust displayed a wider change particle diameter, notably larger than isodust. The distinctions suggest that finer dust particles are charged, stirring attractive forces on larger particles. The variations attributed to the different origins, with isophile test dust spanning particle size from 1 micrometer to 80 micrometer. Surface profiling assessed the surface roughness of glass, PUF and pH thin film on glass and dust surfaces, revealing porous structure in the PUF and enhanced absorption. Investigated the dynamic behavior of naphthalene and benzopyrene on both glass surface and dust in confocal fluorescence microscopy, assessing concentrations range from 10 to the power 3 to 10 to the power 8 molar for both compounds. At concentration degree, the distribution density and fluorescence intensity markedly decreased, observed in both blank and dust mixed samples. Notably, the fluorescence distribution differed between glass and dirt at the same concentration, with naphthalene and benzopyrene exhibiting significantly stronger fluorescence on dust surfaces and concentrations below 10 to the power 6 molar. Dust tip surfaces displayed a more even distribution, indicating even absorption, while naphthalene concentrated on glass. Fluoridization studies over time revealed that higher temperatures predict emission as SVOC particles more readily from source materials into the air. Moreover, the influence of relative humidity demonstrates that relative humidity level above 50% resulted a notable decrease in fluorescence intensity, potentially indicating increased emissions and exposure with higher temperature and humidity levels. So that the fluorescence intensity decreased over time on both glass surface and to the sample, the intensity of both naphthalene and benzopyrene on SRM dust were lower than on isodust. This can be explained by the fact that SRM dust is a type of house dust that certified as having other pollutant compounds present. For PAH to absorb this dust, they must compete with those substances. In other words, the substances present in the SRM dust compete or interfere with absorption of naphthalene and benzopyrene. Exploration of interaction between naphthalene and benzopyrene on glass surfaces using ATI-FTI imaging yielded findings consistent with the confocal microscopy results, with concentrations ranging from 10 to power 3 to 10 power 8 molar. For benzopyrene, I focused on the infrared peak at 840 cm-1 to detect decreasing concentrations, which display a gradual reduction in signal intensity from 10 to power 3 to 10 power 8 molar. The same spectral trends were observed for naphthalene, with infrared peak at 1502 cm-1 serving as marker recognitions at different concentrations. However, more notable reductions were observed for the characteristic infrared peaks representing benzopyrene and naphthalene. Moreover, I investigated the interaction of the volatile compound with dust surfaces, isodust and SRM dust, revealing uneven distributions for both dust types, as shown in the figure. Time-dependent volatilization was recorded as 0 days and 21 days, indicating discrete intensity in the characteristic bands for both naphthalene and benzopyrene in dust samples. Comparatively, degradation on glass surface exceeded that on the dust surfaces, suggesting that partial absorption of impurities by the glass surface. Independent evaporation was also investigated in this study from 25 degrees Celsius to 50 degrees Celsius. The intensity tended to decrease gradually, as shown in the figure. With the substance on glass, the intensity decreased significantly. With benzopyrene, the intensity was typically reduced by around 40% and 30% on glass and dust surfaces, respectively. On naphthalene, the decline was about 50% for glass surface and 5% for the dust surface. In our investigation of naphthalene and benzopyrene evaporation over time, we found that the minimum times required for naphthalene and benzopyrene to reach dynamic equilibrium were approximately 92 hours and 250 hours, respectively, due to benzopyrene's larger molecular weight. Following equilibrium, the airborne concentrations of naphthalene and benzopyrene on glass surface were measured at 23.16 microgram per meter cubic and 1.53 microgram per meter cubic, underscoring benzopyrene's limited capacity for airborne dispersion consistent with FTI and confocal fluorescence measurements. The study explored absorption and distribution of naphthalene and benzopyrene into the air after initial absorption on various surfaces, including glass, dust, and PVF, conducted within sealed environment. The measured gases concentrations on the surface were 11.22 microgram per meter cubic for naphthalene and 0.82 microgram per meter cubic for benzopyrene, while on the POF surface, concentrations were 0.99 microgram per meter cubic for naphthalene and 0.2 microgram per meter cubic for benzopyrene. Notably, these concentrations on dust and POF surfaces were lower than those on glass surfaces, despite the addition of an identical amount of pH. This can be attributed to greater absorbing capability of dust and POF, coupled with the surface morphology which, unlike glass surfaces, offers greater volume and absorptive potential for pH, effectively acting as a reservoir for trapping SVOCs from the air. The last part will be conclusion. Focus on the physical-chemical dynamics of pH on both glass and dust surfaces, employ spectroscopic and GCMS methods. Shave thin films of naphthalene and benzopyrene, two pH compounds, were detected in the air and on glass surfaces. Utilizing confocal fluorescence and infrared microscopy, we monitored the presence and changes in the aromatic species on glass surfaces. Infrared mapping based on the vibrational characteristics of these pH provide insight into the dynamics. Gas concentrations were measured using GCMS, and isotope and SIM dust were tested to assess pH absorption on surfaces. My study holds practical implications in various fields, including environmental monitoring, industrial applications. pH are common found in the environment and associated with health risks, and can be monitored and evaluated through the study and the thin film layers on different surfaces. This research can inform strategy for remediation and cleanup efforts, as well as policy and reduce pH exposure and enhance public health. Listening.